be explaining HPC composability, what it is, why it's beneficial. I'll explain what OpenFabrics Management Framework is and how it manages HPC composability, and then I'm going to give some examples at the end here. So let's go to slide 4. Yeah, right there, perfect. So we have composable disaggregated systems, and if we look here, there's a lot of things going on in this picture. We have pools of memory, and we have remote resources. Everything in the local region is connected by CXL switches, and we have an RDMA network linking more remote pools of resources. We can connect to and access resources over the CXL and RDMA networks. These resources are disaggregated. That means they're separated components, and we're trying to link them together so that we could theoretically compose on-the-fly component resources in chassis, systems, and platforms. I'm going to go into more details as we go forward. Let me get my, here we go. Okay, so next slide, slide 5. This is an example of what I'm kind of talking about, composable systems. This is a CXL switch, set of them. On the left, we have host 2, and if you can look at it closely, you'll see host 2 is connected to fabric attached memory number 1 through a CXL switch. Host 1 is attached to fabric attached memory number 2. And then we go on to the right side, and we can actually aggregate our memories together. For instance, we have host 1 attached a portion of fabric attached memory number 1 and fabric attached memory number 2, and then host number 2 is connected to a portion of fabric attached memory number 1. Okay, next slide. So on the right side of this picture, we can see a typical HPC architecture. We have each node containing a set of CPUs, some memory, and accelerators. We link the nodes with a high-speed fabric, network fabric, and that's how you do your computations. One issue is that you need to over-provision the nodes to assure that as an architect, that you allow for application codes that are requiring the resource components. All of the nodes are powered up. They're all drawing energy. All the resources in the nodes are drawing energy at all times. Not all the applications are going to be using those resources. So basically, since we're over provisioning our nodes, we're actually wasting energy. We want to mitigate resource over provisioning. Therefore, we can reduce energy consumption and cooling costs, and then we can add resources where we need to, as we need to as well. So for instance, we have nodes that might need more memory, or we have computations that might need extra accelerators or so on and so forth, or more CPUs even. So let's go on to next slide, number 7. This kind of shows you what I'm talking about. So CXL3 is a peer-to-peer switch. If you think about it, peer-to-peer connections allow you to access all the resources equally, and all the resources are connected to the CXL switches, and they're all equally available to each node. In this example, I share GPUs connected to switches, and even in separate boxes, I theoretically can share CPUs, memories, as if some resources aren't being used by a different computation, I can share those resources. Further, with management, I can reach across this RDMA fabric and switch and pull even more resources in an emergency. You can do that. Sometimes the applications can run out of memory. In another example, for instance, I might have oversubscribed a physical node with too many containers. In another example, parallel I/O servers might be overloaded and need more resources to keep operating. For instance, Lustre often uses Z-pools and ZFS adaptive replacement caches, and these caches are susceptible to overfilling and that can cause thrashing. The MDS and OSS service can cause a lesser failure in those situations. Go to the next slide. So how do you manage that? How can you manage things? Here is a diagram of the DMT redfish tree. So we can leverage the DMT redfish tree to do the management. We've got, if you look here, we've got systems, we've got fabrics, we've got chassis, and in each of those has separate categories. For instance, our fabrics will have switches and endpoints, and our chassis will have media controllers and memory controllers, and we'll have switch ports, and we can manage all that stuff through a redfish tree. Using redfish trees, we can keep track of information on features. We can check current resources allocations. We can look at connections, events, environmental conditions, and security keys. And on top of that, Swordfish, which kind of appends to the redfish tree, provides us with storage-related extensions like NVMe device management, file, block, and object storage information. And you access redfish information through RESTful connections with HTTP and HTTPS. So let's go to the next slide, slide 9. This shows a build out of a redfish tree and how you would post information to it. So for you'll look up at the top there, you see redfish, the root path is redfish v1, and then I append on what I'm wanting to address. For instance, I can go systems, fabrics, chassis, and then I'll get a collection instance for those type of options, and then once I get those collection options, I post the file through to the redfish tree. Next slide. So I'm going to leverage. So I leverage the redfish and swordfish trees to manage an HPC system, and this is how I'm going to do it for composability. In the middle, you see the OFMS services, the OpenFabrics Management Framework services, and I've got resource inventory, I've got management, I've got configuration, current configuration, I've got authentication information, access control information, and a critical piece is events and logs. I'll explain those as we go along. The OpenFabrics Management Framework acts as a central repository for the redfish and swordfish information on an HPC system. The OFMF leverages redfish and swordfish endpoint emulators, so we don't actually have to communicate to the resources every time we want to get information. The emulators provide that to us. Queries are made originally to the resources, and anytime we have an event that's reported to us, we'll go about and go back from the OFMF and do a query to the resource, gather that information, we store it in the middle. The OFMF gathers the information, and then it interacts with the hardware to allocate resources, networks, and security information. Let's go next slide. Oh, okay. Okay, that wasn't the slide I had, but let's go one more slide, I think. Oh, we're missing a slide. Okay, let's go back to the first slide. So, oh yeah, go back to that one that you had just a second ago. There you go. So, yeah, we skipped a couple slides here. Slide 11. So how do we do this? On the right side, you'll see some network fabrics, and we can use these agents for special hardware, and we need all that information. We need that control for a composition manager, which we'll be talking about on the left side. So on the right side, you see technology-specific agents. These agents are designed to translate redfish operations that the OFMF needs to control stuff and also gather information from the fabrics on the right side. And these redfish operations are kind of common features, and they allow the vendors to hide their secret sauce and special features from the composable system, and then they expose the common features and features they want to provide. So we'll go to the next slide now. There we go. Okay, so this is how this all operates. We launch our agent. Our agent runs independently of, in this case, a subnet manager. And the subnet manager comes up, and then they communicate to each other. The agent says, oh, I see you're alive. I need some information on whatever the network fabric is. And it says what's there, what endpoints are there, what's maybe on some fabrics we can find out what the endpoint contains, if it's got NVMe memory, how much memory and stuff it has on it. But definitely we'll find out what endpoints are available, what switches are available. We find out what switch ports are there. All that stuff that you normally would get out of a network fabric gets provided to the agent, and then the agent translates that information and sends it over as an event to the OpenFabrics Management Framework, where it gets stored for later usage. Anytime there's a change in the fabric, we get an event, and that gets updated to the agent, and the agent, again, in turn, provides it over to the OpenFabrics Management Framework. Next slide. Here's an example of this. So let's say we brought up our agent. Our agent comes on. It communicates to the subnet manager and says, "Are you a subnet manager? Is this information on a subnet manager?" And if it's a yes, and it gets that information and says, "Oh, here's a subnet manager," provides it to the OpenFabrics Management Framework. It goes and as a subnet manager recursively crawls through a fabric and provides us with information on endpoints, links, switches. That information gets updated and put into the OpenFabrics Management Framework. If we find out information on some fabrics can provide information and control memory chunks, it'll do that as well. Next slide. Here's an example of the Gen Z fabric, which does endpoints and the whole fabric. So we have a Zephyr. Zephyr is the subnet manager for Gen Z, and Zephyr is going through, crawling through the fabric and getting all the information, and then in turn it comes back to the agent. The agent translates that information over to the OFMF services, and then I can use that for composition and fabric attached, and a fabric attached memory manager, and then in turn to an administrator or a client. Next slide. All the on NVMe fabric, NVMe attached to fabrics, I would get the fabric node IDs that connect to that NVMe. I'll get the the ID of the endpoints. I'll get memory chunk size. I get minimum chunk size, maximum chunk size, and then I can provide that to the Redfish agent too. Next slide. So here's where the composition comes into play. On the left side, we have fabric resources monitoring. We build up a composition manager that talks to the OFMF services, and then we also have resource control. We have storage fabric control, and then we can use those events and logs to keep track of things as we go through it. You'll see events all the way through the whole center of the management layer. Next slide. So I'm going to take a couple examples here of creating a dynamic HPC system with composable systems. This would be a runtime dynamic container. We've got a container deployer, and we've got a workload manager. And those would go out, for instance, saying, "Oh, this container needs 6 GPUs to run its batch job per node." and it would, or I need this much memory per node or whatever. It'll go over to the composition manager. The composition manager in turn queries through Kafka or Red, in this case, RabbitMQ or Kafka as a message queue because you want to be able to scale it. Goes out to the OFMF and says, hey, what's available to me? And then the OFMF says, oh, I've got these resources. We have these resources, and it says, okay, what's close to me? Tell me about these links, and et cetera. And the OFMF provides all that information, and then in turn, the composability manager will say, okay, I want these resources, these links, compose a system for me. The OFMF goes out to the agents or out to the hardware directly and composes the system up, updates its database basically in the Redfish tree, and then provides that information. I've got an OK to the composability manager, and the composability manager goes back to the container and says, okay, everything's here, ready to go. Next slide. So this is a little bit blown up example here. We've got, for instance, I just took some containers, and the container engine went out and requested the information from the composability manager, and the containers got supplied through the fabrics, through my high-speed RDMA links or high-speed network, the CXL switches, and then we've got resources as far as CPUs and memory provided over to the containers. Next slide. This is an NVMe. Again, this is another kind of description. So on the left side, we've mapped out. The OFMF has a map of the redfish and swordfish that it provides to the composability manager. And in turn, on the right side, the actual hardware connected to the networks. And then in the middle, we've got blocks to show storage, and we're using those blocks to build out our fabric attached memory for whatever we need. Next slide. So another example on demand. This is kind of a killer app for this, I think. We have an on-demand node local parallel file system. In my case, we've been working with them a little bit here at Sandia. We've got a management server with metadata storage and client on it, and then we've got compute nodes. All the compute nodes are containing storage, and they're also clients for node local file system, parallel file system, and that provides local storage for runtime jobs, and it builds up and tears down as you get Slurm allocation is what we're using them with, and everything's kind of linked together with InfiniBand. Next slide. On the left side of this diagram, you'll see what we've currently got is we're taking resources, in our case, either direct attached storage or we're using RAM disks, and that kind of takes away some of the RAM from our run jobs, so we have to be kind of cognizant of that. On the right side, however, with the composable system, we add the resources in as we need. We can do that with containers too. We can actually use these on-demand file systems with containers. You could have 6 containers running totally separate file systems, and we're all linking all these all the NVMe memory together with CXL switches cross-pointed, so we can allocate whatever we need to fill in the gaps for what we need for memory or resources. It kind of works with it kind of takes that dynamic that dynamic file system and exploits it in new ways. Next slide. So again, everything comes back to the OFMF. being a central repository for all the information. We're managing everything out of the OFMF. The composability manager uses the OFMF to get information and control the resources that are available on the right side. We've got, like I said, we've got input on technology-specific agents. We've got input on composability from the composability manager, and we've got input for monitoring, all going back to the OFMF. And then the OFMF controls everything. Next slide. Any questions?
All right, thank you, Michael. Appreciate that. We do have a couple questions here. One came in just on the last slide in terms of what is the performance in such a config aggregated?
So we're working that out. There's been a couple. If you go back to the next previous slide. So we're looking. This is probably not the best view, but we're looking at a couple things. So we want to make sure we're low latency and high bandwidth with our network links. Obviously we keep the pools that are local. Let's see if I can go back to slide 4, maybe. So the point of this picture was to kind of show that in a way. So if you've got a local pool of memory or local resources shared over a CXL switches, the idea is that you'll have lower latency than you would reaching over to the other side of a network, RDMA network, for instance, and trying to gather other resources through that through those RDMA switches. Again, everything's still low latency and high bandwidth, so but there will be a little bit of latency and bandwidth over there. You want to keep everything local. That's the same idea with that node local file system. You're keeping everything local in the area, and then using the resources there. If you need to, though, let's say we ran out of memory in our local pool, and it was an emergency type situation. Instead of bailing on whatever application or run is whatever or need is at the time, that you'd be able to pull those other resources across the network and utilize them as long as they're available.
Okay, thank you, Michael. I am not really able to check chat right now. I was just going through the Q&A. I'm glad we're able to work this out with your slides. Really appreciate the presentation, and if you can hang on for a bit and see if there's any questions that you can answer via the
Sure.
chat or the Q&A, that'd be great. Thank you again, Michael. Michael Aguilar from Sandia. All right.